just a recap of the last lecture. So last lecture, we talked about brittleness of deep learning networks. And the problem was that if you add a small perturbation can cause state-of-art deep networks to misclassify an image. And that's a serious problem, which means an adversary can attack, and that becomes a security concern. And I gave you lots of examples of adversarial examples, and these are because machine learning is being used in the practically in the real world life, and including self-driving cars, biomedical image analysis, and video surveillance monitoring, and all these critical applications. So if this brittleness occurs, so that's a serious concern. So we talk about different attacks, like fast gradient sign method, basic iterative method, momentum iterative, FGSM, projected gradient method, and LB, FGS, Carlini-Wagner. There are lots of different attacks, and also deep fool. Then these were like image dependent attacks. So given an image, we can generate a perturbation and that image will misclassify. But then there are attacks called universal attacks. So that will work for any classes or any images. We briefly discussed that, and we will discuss this paper also in detail. And then we talk about also one defense method, that if you can make a network which will detect this attack and rectify that, and then you will defend that attack. So today I'm going to talk about that we can train the deep neural network networks which are robust, and these are the adversarially robust network, and they have lots of good properties, and that's kind of trying to address some of these concerns. Okay, so so I'm going to talk about 4 papers from same group at MIT, Professor Madri's group, and let me take care of this thing here. So this is the first paper, which was published in NeurIPS last 2019. Image synthesis with single robust classifier. Another paper, robustness may be at odds with accuracy. And then third paper, learning perceptual aligned representation via adversarial robustness. And then fourth paper, adversarial examples are not bugs. So I will go through quickly. These are pretty detailed papers, and if you are interested, you can read them. But I want to give you a broader overview of these 4 papers. So before that, so let's review when we train a classifier, what we have to go through. So as you know, that training a classifier, we need a data, and Xi are samples from the data, and Y are the labels. So we have, say, M samples, that's the data, and we want to train a classifier which will take a data point from X and map it to the k-dimensional vector. Suppose we have k classes, and give you the probability of each class which can be present in that particular image or particular sample. So now in this case, we have to look at the loss because we have a ground truth, which is given, the label, and then we have the prediction from the network, which is the h theta of x, and we want to compare the prediction with the ground truth, and that comparison is a loss. And we want to learn theta such that this loss is minimized. Okay, so the theta are the parameters of the network. So this loss will take the image and its label and map it to the real number 0 to 1. So where we have lots of examples, say m examples. We will get a loss for every sample, and we add up the losses for all samples, divide by m, and we want to minimize this loss. And by minimizing, we'll find the theta. We want to find the theta so that this loss is as small as possible. So that's a standard method of training a deep neural network. Okay, so typically what you do is use a gradient descent. So you take the loss L, find its gradient with respect to theta, and this you do for the batch size of beta. We add up these losses, and then you average that number of items in the batch, and this is step size, and you take the step in that direction, and you change the theta depending on the gradient, and you keep doing that. That's our stochastic gradient descent to train the classifier. It's a standard thing. That's what you have learned. Now we are going to talk about the adversarially robust classifier, and those classifier hopefully will be better than the standard classifier. Now, in that one also we want to find the theta, and we will have the training data set, and so we will have number of these training examples. So we'll have pair, the image, and the label, and from this detrain is a data set, and we will sum up this loss, which is shown here, and that loss is very similar to the previous loss. That will depend on x and depend on the label, the ground truth label. But we will have one more thing, that we are going to add the perturbation delta to that x, and then we will find the perturbation delta among all permissible perturbation so that this loss is maximized. And then we will do the minimization of this loss. So as you see here, we want to find out what delta we put in here so that this loss is maximized. Then we sum up this loss, and then we want to find the theta so that this loss is minimized. So we are intentionally putting the perturbation to make the robust classifier. So then, and then the same thing as we did in gradient descent, we'll take the gradient of that loss, and then we will add that gradient with the step size to the previous estimate of theta, and we'll keep doing that. Now, as you see that we have maximization here, minimization here. So therefore, we will have two steps. So first step will be that we want to find out what delta we should add so that this loss should be maximum. And second step, once we find that delta star for which this maximizes, then we will put that delta star here. And then second step, we will find the theta so that this is maximized. Okay, so that is our the method. So this is one is the maximization of the minimization of that. I think this should be, yeah, okay, so this is fine. So now in order to find that, as we discussed, we will use typically gradient descent, but we are going to use what is called, we discussed last lecture, projected gradient descent. Okay, so that is one main difference you want to keep in mind, that in order to train a robust classifier, two things. So one is that we want to aid the perturbation. So we have two steps: find the maximum perturbation, which will maximize this inner loss, and then we do the standard minimization of that loss. So then, instead of using the gradient descent, we'll use a projected gradient descent, PGD. So as just a refresher, that we want to solve the optimization problem by gradient descent. So gradient descent is the most easy method to minimize or maximize any function, and it looks at the gradient, and it is unconstrained optimization problem. We have the function, we want to find out what is the value, starting with some initial estimation of the solution, which is the x0. We want to find out what's the best value that this function will be minimized. So this is our gradient descent. Take the function, find the gradient, and then step size, add to the previous estimate. You just keep doing that. So now this doesn't have any constraint, it's unconstrained. We want to find any solution for which this function is minimized. So then the question is that what can we do when we have some constraint? So can we put a constraint that, well, the solution is, of course, the minimum of the function, but it satisfies some constraint, because that's what we have in the adversarial machine learning. So then the answer is yes, there is a method, which is basically PGD, which will do that for you. So PGD, as we discussed before, we are given a constraint, say Q. So we want to start with x0, and we want to iterate as we did in gradient descent, same thing. We take the gradient, step size, we add to the previous one, but to get the new xk plus 1, we're going to project this, and then that is make it projected gradient descent method. And projection is that, well, whatever we get is x here, it has to be satisfied within this norm, and here we have L2 norm. Okay, so that is our constraint. So now comparing PGD to GD, as you see, these are the steps. We start the initial estimate, we loop, we pick the descent direction, we pick the step size, we just keep updating like this. And PGD is the same. We start with some initial estimate, which is within the constraint, and then we find a gradient and we iterate, but this additional step of projection. So that's our PGD method. Okay, so adversarial by the standard training is that, let's say we have binary classifier. So with these blue one are one class and the green one are another class. Now, what happened when you do the perturbation? So you are putting some perturbation to these samples. So therefore, this sample can move to the other side, to the blue side. And this blue can move to the, also potentially move to the green side. So that become a problem. That's why it misclassified. So what that does, that basically boundary of classifier is changed. So if you have now this boundary to incorporate this, then this is a robust classifier. Okay, so that's what we are trying to get. So given this background, we are going to talk about these 4 papers. So this is the first paper, image synthesis with single robust classifier. Okay, so using this idea, we'll be able to generate synthetic images like these. We will do inpainting, we'll do super resolution, we'll do paint with features, translation, sketch image. So I'm going to explain to you each of this separately. So, robust classifier, it encodes the priors to the model, preventing it from relying on imperceptible features of the input. Okay, so it's invariant to small perturbation because we are adding the perturbation in our last function, and it ensures that changes in the model's prediction correspond to salient input changes. So here, let's look at that. We want to generate a realistic image. You might have known that you can use a GAN generator adversarial network to generate images, and these images look very realistic. So this is another way actually to generate synthetic images, which looks realistic. So what we are going to do, that we will have the robust classifier. We'll take that and we'll maximize the probability of particular class from the robust model. So that basically we'll do a targeted attack. And so the way we are going to do it, that we want to find X prime such that the image we get X prime, the classifier say label Y. Okay, so we'll start with some initial estimate X0, and we will have this loss function, and we will put the image to the classifier, and we want to make it that it classify as the Y class. So it's a simple minimization problem. We'll use the PGT to do that, and we can determine X. And so here's the example. So we start with this image. And so let's say we want to, from this original image, we want to make it a dog. So our Y here is dog. So we will find out what image, how we change the pixels so that it is classified as a dog. And it looks like that. So remember that when we train a classifier, we have a loss function, we differentiate it to find the weights. Now here it's already trained. So given a trained robust classifier, we want to find out, given an input image, what changes we make in input image, how we change that image so that it's classified as Y. And starting from here, we want to classify as a dog, it will look like that. Then from here, classify as a cat will look like that. So you're making these changes, and this is the way this image is going to change. Similarly, we start with this image, it's going to change. So these images kind of look pretty realistic, but it's very different way we are synthesizing these images. So now we started in the previous example, that image on the left, but we can look at actually a distribution for an image, and we can just sample the distribution. So that will be your X0. So we will say have a Gaussian distribution for that class Y, and for which we will have mean vector, we'll have normal distribution, Gaussian distribution with a mean vector and the covariance matrix. So this is a mean, and this is a covariance. So we can take a bunch of the images in that class. We find this mean and covariance, and then we sample particular image from there, and we use this method to find the image X prime so that its particular label is Y. So here are the synthetically generated images using this simple minimization from a cliff class and fish and potatoes and so on. So they look pretty interesting. So we can actually generate more samples. These are different samples of dog, different sample of bird, again using the same thing here. And it's a pretty simple thing. We have a loss function. We apply PGD, differentiate this with respect to the pixel image, and those pixel changes, which will give you this loss function minimized for that class. So that's one example. Other is inpainting. So inpainting is a task that we can recover large corrupt region from an image. So here's the example. So we have original image. So somehow this was corrupted here, and we want to recover this back. So this inpainted image. So that is the so that ideally it should look very similar. This is doing reasonable job, but it's not perfect, but that's fine. So again, we can do the same thing. We want to find out X prime so that the classifier minimizes, classifier recognizes that X prime as a class Y. This is our class Y. Okay, so what we need to do now, we want to only change these pixels which are inpainted, but which are blocked. We don't want to change the rest of the pixel. So therefore, we will have this additional loss that M is a mask. These are the pixels which contain mask. So we want to 1 minus M is the rest of the pixel. So we don't want to change those pixels with the rest of the pixels. So that's why we have 1 minus M and X minus X bar. We don't want to bother these, but we want to minimize this so that we want to change these pixels, and that's what this is. So that is inpainting. And as we discussed, that this is the loss function, and lambda is just because we are combining these two losses. So it's like a Lagrangian multiplier, and we want to minimize that. So, so there are more examples. So this original image, this corrupted, you saw that. It's another image. This is the inpainted. We recovered this inpainted. This looks pretty good actually. And here it's recovered here. This one here. So, and there are more examples of this. So it's pretty interesting. It's very simple method. You could do that. Okay. So another example is that we are given a horse image and we want to convert to zebra. So this is image to image translation. That's actually there are lots of papers on that also using standard gain. So for using this robust classifier, what we do, we first train a classifier which can distinguish between source and target. Now here source is a horse and target is zebra. And so first we do that. Then what we do, we want to translate input from source by maximizing the predicted score of the target domain. So the same idea here, okay? So here now Y will be our target domain, here will be zebra. So if you do that, then we can generate these images. We can take the zebra to horse, April to orange, and winter to summer, and so on. So we can also use a super resolution. So super resolution is that you take a low resolution image and convert it into high resolution image, okay? So low def to high def. So again, same idea. So we want to come up with X prime, which is upscale version of the low resolution. XL is low resolution. And again, we have this constraint that they have to be within this epsilon. This upsample version of the nearest neighbor. So now we are given the low resolution, and we want to get a super resolution, but the constraint is in terms of some upscale version of the low resolution. And there are many different ways to upscale. So here they use what is called the nearest neighbor. So let's say we have a 2x2 image and we want to get the 4x4 image. So what we do, we just take, we just take the 1 pixel, map it to 2x2. So this was 1, so all become 1. This was 2, all 4 pixels become 2, and so on. That's called nearest neighbor. So if you do that, in this case, as you see, so we are given low resolution image, so we upscale that using nearest neighbor. Now we want to come up with X prime, which is using this, which has this class Y. So, and this is the example here. So we have here the CFAR original images. The next second row shows the, why this keep changing here? Okay. Second row shows the simple bicubic interpolation using super resolution. And this is using this robust classifier. And it is increased by 7x. This is example from the ImageNet, it's increased by 8x. So another application of this is interactive image manipulation. So we say we have a sketch and we want to generate a realistic image. So these are the realistic image generated using, again, the same idea of the loss function given a class. We want to minimize this using PGD. Other thing we can do, that we can do feature painting. What does it mean? Let's say we have an image like this, and we want to make all the pixels belonging to these from the duck. We want to put that texture. Then we want to take all these ground pixels, the grass, and all the pixels here to the sky. So we can do that. Instead of now we are looking at before, we are looking at taking the image X prime and mapping to the class Y. So here what we are going to do, the representation of X prime, the particular feature of that representation, we want to maximize that. And again, we want to do that only for those mask pixels. So only suppose these pixels for here. So that's why we have constraint. We don't want to change 1 minus m. We don't want to change the other pixels here. And that's the way it works. Okay, so this is the pre-final layer. Before the final layer, that's representation we have, and we want to take the particular neuron and get its features, and we want to change those so that these pixels looks like duck here, these pixels look like grass, and this look like sky. So it's very interesting, very simple, robust classifier using these PGT kind of minimization. So now the second paper, which is called Robustness May Be at Odds with Accuracy. So as you know, by now, you should be convinced that there's a tension between adversarial robustness and also the generalization. That's why if we are take, then we are reducing the accuracy of the classifier due to the adversarial attack, and that was the problem as we discussed before. So training robustness models may be resource consuming. As we say, well, we can train a robust classifier, but the problem is that it will have the extra cost because we need to put that perturbation, because there are 2 steps as we discussed before. And so that's the what we have here. And so it also, when we do that, it reduces the accuracy of the classifier. So I'm playing with this thing. How to? Okay, now it's good. So robust classifier learns fundamentally different feature representation than standard classifier. Standard classifier is the first slide I explained to you. Simple gradient descent. Use it, but the robust classifier, that we are adding perturbation. So now robust model tend to align better with the salient data characteristics, and they are kind of similar to human perception. And also the feature learned by optimal standard, optimal robust classifier can be very different, okay? So other point is that, as we mentioned, that we have these extra resources needed for the adversarial training. So that's why it needs more training time. So now, just to recall, this is the way we are training the robust classifier. So now as training data increases, the standard accuracy of robust models drops below that of the standard model. So that's the point here. So here's an example of the MNIST. This is the training data, and this is standard accuracy. So now if we use the standard classifier, no robust, so this is the accuracy or changes. As you know that when we are increasing number of training example, the accuracy increases, which is what we expect. Now, if we train a robust classifier, these are different robust classifiers with the different perturbation. As you see that these one actually have high accuracy with few training samples. So this is another example, C410. Again, here we are showing the black one is the standard classifier, and these other ones are the robust classifier with these different perturbation. Now here, the robust classifier actually are not better than the standard classifier. And the same thing about the restricted ImageNet. So from here, the point is that when we have few samples, then adversarial training in this case actually is helping. It has a positive effect because it's generalizing better. We have a better accuracy. So it is in a way serving as a data augmentation. As you know, if we do data augmentation, which means we take the one sample and do the augmentation, rotation, and cropping, and so on to increase the number of samples. So here, perturbation, when we are adding, in this case, we are kind of doing the data augmentation because for the few samples, then this robust classifier can do better. But in this case here, we already have quite a few samples, so it's not making much difference. So if as the training data increases, standard accuracy of robust model drops below that of standard model. Okay, so that's one point. The second point is that there are some benefits of adversarial robustness, and that can be viewed as a method to embed certain invariants in the model. And robust models are more aligned to human vision than standard models. And so we can look at the loss gradient, how they look like. So what we are showing here is the MNIST data set, and these are the original images. And we are showing the gradient at each pixels. Now, when we have robust classifier, whether the L infinity L2, then the gradient is located at the right places where the digit is, where the useful information is. It's a meaningful in both cases. but as compared to standard classifier, gradient is all over. So that is the problem, that what robust classifier is relying more features, more information, which is kind of aligned with the human perception. And another example from CFAR, again, these are gradients for the loss gradient when we train the robust classifier. As compared to standard classifier, these gradients are not that meaningful. Same thing for restricted ImageNet. So also these examples exhibit some important data characteristics. And so what we can do, if we apply the project gradient descent to given test image, to find the image of the highest loss around that original image. So, so this procedure will change the pixel that are most influential for the particular model's prediction. And that will tell us more information. So here we have original image of primate, and we want to change it. We want to make the changes so that it becomes like in maximum change which we can make, that it changes. So this is the maximum change we can make, and it becomes looks like this, and it is classified as dog. But this is a standard classifier. Now when we do the same thing for L infinity robust classifier, L2 trained classifier, the changes here results in this, and this looks like actually dog, and the classifier says it's a dog. So which is pretty interesting. And here the classifier says dog, but this actually doesn't look like dog. Okay, so that is important. And the same thing here, we take an image of a bird and we make the perturbation maximum changes and results in here, and then classifier says a turtle. But when we use the robust classifier using L infinity train, it results in this, and it is classified dog and looks like a dog. And this is in L2, it turns into cat, and they actually look like a cat. So which is, I think, the important point, that these images produced for robust models actually capture the good data characteristics and appear to similar to examples of different class. But in the standard one, they are not. That's not the case. So other thing also is that if we take the original image and PGT, a text image, and we can do a smooth transition, and those transitions actually are meaningful, and this is called interpolation. So we started here, we result here, but this is the different interpolation between two images. And as you see, this is very smooth transition. And that's what they actually show this in the GAIN examples. The image is generated from GAIN. You can show this simple, nice transition. And the same thing happening here in the robust classifier. So another example, we start from here, we train back here, but in between we can go these kind of things. So which is interesting. Okay, so the third paper we have is the adversarial robustness as a prior for learned representation. So so now here, as we know, our important goal is that we want to learn versatile representation, and we want to get a high level feature representative input data. That's the ultimate goal, what we are trying to do in the training a network. Now, representation of a standard network has shortcoming that prevent them from fully realizing this goal. Now, if we do the robust optimization, then we can enforce these priors on the learned features so that these feature representation are meaningful. And so we will show the representation learned by robust models can address these shortcomings in the standard classifier, and we can make significant progress towards the learning high-level encoding of inputs. And so also these representations are approximately invertible, which means that we can allow for direct visualization and manipulation of these salient input features. So let's look at how we can do that. So the limitation of standard representation, that images with nearly identical representation at drastically different content can be constructed. Okay, so let's say we sample two images from a data set, X1, X2, and we want to optimize one of them to minimize the distance in the representation space, so that like this. Okay, so we have X1 and X2. We take the representative X2. So these are the layer before the last layer. We are looking at that representation. And we want to take the X1, add some perturbation, so that representation of X2 and X1 plus delta is very similar. Okay, so we want to find out delta so that this difference is minimum. Okay, so here's an example. So we took, we have this X2, we came up with, we took some X1, which is not, as X2, very different class. Then we change that X1, come up with X1 prime, and now representation of these two images, which are very different, they look exactly the same. So that in that layer, that particular neuron has the same representation, same values for these two images, but they are very different. So that's the problem. So, so the representative inversion can recover an image that maps to the desired target representation. So now, as you saw the problem with the standard model, the robust model actually doesn't have that problem. And resulting image for robust models are semantically similar to the original images whose representation being matched, and which is a good property. So let's say we have a target image X2, and these are the source images X1. These are very different images. Some are random noise, some are these other things. So then again, we want to take X1, we want to come up with X1 prime, we want to make some changes, we want to add some delta to X1 so that its representation is similar to this image. And if you do that for the robust classifier using this method, as I showed you earlier. So again, all these optimization will be PGD. You have a function, you want to minimize that, do the PGD, okay? So now for this one, X1, this is X1 prime, using robust classifier. So representation of this and this is same. And which makes sense, it actually looks similar. Starting with this, we make changes to this, we add the delta to this, it becomes this. Now the representation of this and this is same. So same thing for this one. Even with the noise, we start with the noise. We make changes to this this is x1, and we make changes to become x1 prime, and then it looks like that. Now representative of this one and this one is same, and the same thing, which is pretty interesting. It's very, very nice. So now if you do that for the standard classifier, so then starting from source here, then it becomes like this. So the representation of this image and this image is same, which doesn't make sense. And the representation of this image and this image is same, and like this. So which is the problem here? Okay. So this also works for the out of distribution inputs. So let's say target is these images. And so these are the random images from the test sets. So then source, we have Gaussian noise. So that's our X1. Now we take the Gaussian noise and we use that, come up with X1 prime, results is this, and using this same idea here, that the representation of this and this is same. So X2 is this one. We start from Gaussian noise. We come up with delta. We add to the Gaussian noise. We keep doing that, for which this minimizes, and we get these. And this is amazing. This is actually, these are meaningful images. It makes sense that this and this represent the same, and same here and here. Of course, there's a little difference, but it's still meaningful. So that's good. So this is also true for the out of distribution. These images from are outside of training distribution. So these are your target, and again, start with Gaussian noise. Sorry. Then you can get this result here. So which is good. So other thing we can do, that we can find out X prime, the input image, such that the particular feature is maximized, activation of particular feature is maximized. So we want to take the X0, we want to add some delta, so that particular feature give you a maximum response. So we want to find out X prime like that. So here is the example. So if we start with the X0 like this, and these are different features, so we want to find out that this particular feature will be maximized if the input is like this, and this other feature will maximize the input is like this, and so on. So the seed is X0, we start with this kind of image. Then as you see, all these features are, giving maximum input to different kind of images, so then if the seed is random, again, these are the images for which those particular features will give you maximum. So it's kind of similar here, as you see that even seed is X0 or seed is this, you get a kind of similar images give you the maximum response. So that is for the standard, but when you look at, that was for the robust classifier. But if you look at the the standard classifier, then that give you these kind of images for which particular feature is maximized, and these are not that meaningful actually. It's pretty kind of noise. So so these concepts, they appear consistently in test input image that most strongly activate their corresponding coordinates. And we can look at the restricted ImageNet data set. So if you look at the 444 feature in the ImageNet trained classifier, which is trained robustly, then the this image, starting with the noise, this particular feature will give you maximum response when this input image is given. Now, when we inputted the real images like this, it gives you maximum response. So it makes sense. As you see, this is the image with the fish and so on. So these images give you maximum response for that particular feature. And when you input these images, it gives you the least response, which makes sense. They don't look like a fish. Okay. So again, we start with x0, we add a delta, and we find out what delta we want to add, that this representation become the maximum activation, give you maximum, and we have to select which feature which we want, because there are lots of features. Okay, so now this one is feature 939, and starting with the noise, this is the input image for which this feature give you maximum response. Now, when we input the real images, it gives you maximum response, most activated, which makes sense, it looks like that. But when we input these, it gives you least response. So that's that. So then we have the last paper, which says the adversarial examples are not bugs, they are features. So in this one, what we are going to talk about, that these adversarial examples exist due to the presence of non-robust features, because these standard classifier, they are somehow utilizing non-robust features, and then we can fool them by giving them adversarial examples. That's first point. And the standard classifier works pretty well. They give you very high performance, but they are brittle. And the features they rely on, they are not comprehensible to humans, as you have seen the examples. So main point here is that we usually train classifier solely to maximize accuracy. We just want classifier which give you maximum accuracy. And so what classifier is doing, that using any available signal to maximize accuracy, even those that look incomprehensible to humans, because the machine, it doesn't care. It says, well, as far as accuracy maximize, I'm going to use it. So adversarial vulnerability is like a human-centric phenomenon. And from standard supervised learning point of view, non-robust features can be as important as robust ones, because their purpose is to maximize accuracy, and that's fine. They get good accuracy. even though they are using non-robust features. So, so what we want to do here, that we want to find the robust and non-robust features and give them some more insight. So what we will do, that this paper is pretty detailed, so I'm going to just talk about 2 subsections. So we want to disentangle robust and non-robust features, and we will show that these non-robust features are sufficient for the standard classification. So what we are going to do here is that we have an image of a frog, training image. We will disentangle, we will come up with the robust data set and non-robust data set. Now, if you take the robust data set, it will give you good standard accuracy, good accuracy on the standard classifier. It will give you also good accuracy on the robust classifier. Now, if you use the non-robust data set, it will give you good accuracy on the standard classifier, but will give you bad accuracy on robust classifier or input, with the perturbation. So now the way we are going to do it, that given an image X, like this one, we want to come up with the XR so that their representation is the same. The difference between representation is minimized. And that way, because we want to maintain the representation, but we want to get other things. And again, representation is the layer before the last layer. So other thing we are going to do is we'll take a training image. Robust features will say dog, non-robust features will say dog. Then we will create an adversarial example and change its category to cat. We'll relabel as cat. And so robust features, of course, will still say dog, but non-robust features will say cat. And we'll use that to train the network. And the way we are going to generate these X prime is that we are going to, as we started with X, we generate X prime. We want to change is label to T, and we want to stay with close to the X epsilon, and this is the loss for the classifier. So now when we do that, so this is the algorithm they give you. It's a very simple thing. So we want to get the robust data set from D. D is the original data set. And so what we are going to do, we'll train an adversarial training on D. We'll get a classifier. This is a robust classifier. And so GR is mapping by CR from input to representation layer. Okay, so GR. So we will start with the DR, the robust data set, empty. And then we'll take each pair, XY, the image and this label, and we will take another image, X prime, from the data set. And we will come up with the Z so that the representation of the X and representation of Z should be similar. The difference should be minimized. And that image will become XR. And we will add that to our data set. Of course, the label is Y because that's where we started that. And this, again, we will apply the PDD. And we'll start from X prime, which we got from here. Okay, that's seed. So then that's it. We'll do the loop for this, and that will become robust data set. So if you do that, then these are the the robust data set from the robust classifier. And these are, if you do the same process for the non-robust, look like that. And then if you look at the accuracy and how it's being impacted. So using those data set, robust and the robust data set obtained from the robust classifier, robust data set obtained from non-robust classifier, we train that classifier and then we look at their accuracy and see for. So we are going to show this for the standard accuracy and standard accuracy, adversarial accuracy with the 0.25 perturbation. So this is first. So this is test accuracy. So if you standard accuracy of the original data set D is very high, but when you perturbed it, then accuracy become very low, close to 100, close to 5 or something. So which is, that's what the take is. So that's a problem. Now, if we do the same thing on the same data set, original data set, now if you have adversarial train classifier, then its performance is very close to the original standard classifier. On the standard, standard accuracy, and this is a little lower when we add the perturbation, which is shown here. So which is pretty good. So again, we haven't used our robust, non-robust data set yet. This is just it's showing that while it's a good idea to use the adversarial training to get adversarial trained classifier, which will work in both cases, standard input images and also the images with the perturbation. It will give you reasonable results. So that was the idea. Now, when you look at now, we are going to use these robust examples. And so in that case, the standard accuracy for robust using these robustly disentangled data set is a little less, but it's okay. And then when we do the adversarial attack on that, then it reduces this much, still is reasonable. Now, if we use the standard training using the robust data set obtained from non-robust classifier, then as you see, after robust attack, the performance really go down. So that's the main point. And that's a problem. And then so that's one thing. And so the point was that this example I showed you earlier here, that this disentangling, if we do, the robust classifier will do well. But if you, even after disentangling, if you train on that data set, the standard classifier is doing pretty bad. So now we are going to look at the second point here. Okay, so so what we are going to do, so we'll show that non-robust features are sufficient for standard generalization, which means that the model, which is trained solely on non-robust features, can give you pretty good results. And so we are going to construct the data set with only features that are useful for classification on are non-robust features. They're not good features, okay? And the way we are going to do is this algorithm they give in the paper. So we have, we are going to get a non-robust data set. We have a data set D and we have epsilon. Then we start with the empty. Then we train a classifier C on standard training data, standard classifier. And then we start with XY from the data set. And we assign a label from the all possible classes randomly, just say class T. That's one way. Other way, we can just take the y+1, just an X class or something. So we pick that label. So what we are going to do, that we will take that image X, we want to generate X prime so that its label will be T. So we are attacking it. We are changing its label. And whatever image we get, we'll call X and R. And again, we are going to use the PGT method, PGT attack to this. And that X and R we will add to your non-robust data set. And we'll keep doing that. And we will have this non-robust data set. So now intentionally, we have changed the class for that image X, the wrong class. And we are going to use this data set to train the standard classifier and show you the results. And this is a data set, and using non-robust classifier, these are when we change randomly the label, these are the images generated. When you use a robust, then we get these images. And then when you change the label deterministically, like as you saw, y+1, just the next neighbor, next label or something like that. So again, these are the images we generate from this non-robust data set. So now the interesting thing is that if we take the training sets and train a standard classifier, and these are results we get. So first is, before we do anything, just a standard, just take the original data set. These are the results. C410, 95%, ImageNet, 96%. So it's good. Now, here we are using completely wrong labels for those images. We train on that, still the performance is pretty good. I mean, it's reduces, but it's reasonable, 63. So it's basically using non-robust features to give you this. So that's the point here that this paper makes. So that's it.